And so we'll get started with Thermo final exam review. One thing I've got a few things pulled up I want to show real quick here. So this is our syllabus, and um, with you guys, with this being an online class, I didn't necessarily have this a day where we spent half the lecture going through talking about the syllabus. And so this is our syllabus, and it's got our information, and there's a very simple course description here. And I know when I first started teaching, a lot of times, if I'm taking, if I'm evaluating a course to see, well, is this transfer equivalent? Is it the same as our thermo? And this is where they would start. And I've learned over the years this is not where you want to, this is not what you want to evaluate transfer credit on. Um, if they're written well, a good syllabus should have some block like this: course learning outcomes, or course learning objectives, or student learning outcomes, or student learning objectives, some phrase to that effect. And they should, if they're written well, they should be structured in this kind of a format where upon successful completion of the course, a student should be able to, and then a set of things that are measurable. Right. And I don't have to go too in depth on how these work, but that's again, and you're going to find some syllabi are not well written, but if they're well written, they should contain some block like this. Now, I want to go through these in just a second. I'll tell you why, but another thing I want you to be aware of here in the state of Oklahoma, if there's ever a concern about will my course transfer somewhere, if you just Google Oklahoma college transfer, something like that, you should find this page. It's the Oklahoma State Regents for Higher Education. This is somewhat unique to Oklahoma, not entirely. Some states have this, but the Oklahoma higher regents, who control all the state funded schools, or at least are the governing authority for the state funded schools, and then the private institutions can also participate and really should follow these rules as well. But this body has put together kind of an organization where each of the different disciplines meet and talk about courses they offer that are common. Thermodynamics is a common course for just about all, not all fields of engineering, but many common fields of engineering. So you should be able to go in this database and you go pick, what subject you want to go look at, and you can go see. These are, for example, statics or dynamics, and we're thermodynamics, right? So this will show you a list of all the places that your thermodynamics should transfer, and it goes on for a couple of pages here, and just about any of your subjects. And so both OU and OSU have their fundamental basic thermodynamics on this list, as well as um, Tulsa and OCCC and a few other places. Um, Now, if you go back to this previous page where you get to pick what database you want to look at, and you scroll down, and there's a block down here that says Appendix, Matrix, Notes, Common Course Descriptions, and that brings up this page here. And we should be able to go to engineering here and notice that if they exist, or that some of these need to be done, but if they exist, there are student learning outcomes, which are course objectives or course outcomes, and they have those here. And what you'll find is every one of those institutions, our outcomes should either match or very, very closely cover these. They're supposed to be one for one. So any of those schools on that list should have essentially the same learning outcomes, right? So I bring all this up because if you're studying for a comprehensive final like this one is, you should be able to go to your syllabus. And if your course learning objectives or outcomes are well written, you should be able to read through those, and they should make sense. And you should have, as you're reading them, you should be able to say, oh, yeah, I should be able to do that. Or, oh, yeah, I could probably do that. Or I understand what they're saying there. Because if you're reading any of these and it's like, I don't really know what that's saying, that lets you know kind of what you probably should be studying for your final, or at least kind of maybe an area that you need to go back and reemphasize. So let's look at these. These are often things that when I do introduce the syllabus on the first day of class, I just kind of I'll point to them and say, these are things, and we're going to talk about these on the last day of class, because if I read them to you now, they probably are just going to be words. But now they shouldn't be just words, because this should be stuff we've seen. Upon completion of the course, students should be able to utilize various methods. For us, we're going to use tabular. We talked about the graphs in the back of the book, and we've also have done, when it makes sense, specific heat content. So tables and specific heat content are what we focused on. You should be able to use those to determine state properties and changes in state properties for different substances. We have done boundary work starting, we introduced it in chapter 2 and have done it substantially since chapter 4. So boundary work and compressible systems. That's number 2 there. Simplify, number 3 is simplify general expressions for the first and second laws of thermodynamics to an applicable version for any closed system or steady flow control volume. And not only be able to simplify, but also be able to use those laws, first and second laws, in conjunction with other laws and principles in order to solve for an unknown value. And if you look at how I've structured the course, how I've tried to teach you guys to approach problems, how I try to grade, I've heavily tried to reward numbers 3 and 4. And to get through number 3 and 4, you have to be able to do 1 and 2. And then the last one is what we've kind of tidied up here the last couple of weeks. We initially introduced the ideal model, the Carnot cycle, and that does apply to either gas or vapor power cycles. So we're always covered with that. But we do go ahead, if we have time and time allowed this semester, to at least talk about one idealized cycle. In our case, we've focused on the Otto cycle, which is an ideal cycle for gas power cycles. So we've done all the things basically. And again, I've shown you, and I bring up the course, what's called the course equivalency program. So if you find yourself transferring out of state, right, somewhere not OU, not OSU, somewhere we don't have good transfer agreements already hammered out, I want you to know this information does exist. You're always welcome to email me and say, hey, Professor Fowler, what was that stuff you talked about? But if you find yourself in Alaska or Minnesota and needing to transfer to a school, you can point to this website and say, hey, look, I took this course. Look at all these other places it transfers to. And by the way, here's information about all those schools do these things. And by the way, as a transfer student, always come in with your syllabi. Like you should go through and make a PDF of all your syllabi, or go back and ask some of your professors for some of your syllabi in case there's ever a question about, is this going to transfer? At least you can show up with the stuff in hand. You don't have to wait on one of us to get it to you. Okay. I'm going to get off my, that's a bunch of good information. It's not necessarily what we need to focus on here, but it is important and it bears mentioning there. So let's talk about then final exam in terms of logistics. I've given you information on Canvas, but it's okay to go over quickly here. It's just like normal, it's open book. One sheet of notes, calculator. So standard rules apply there. A few things are different. One is take your exam in testing center, in the testing center, before, I would start before 4 p.m. on Thursday because you get 2 hours. I will go to the testing center and I will pick up around 6 p.m. It won't be before. It might not be exactly 6, but I would not gamble on me not getting there till 6:30. Get there. And the other thing is I guarantee you don't want to be in the testing center on the last possible minute before the end of finals week. You don't want to be there after. It's going to get pretty busy, right? And the closer you get to closing time, it's going to get busier. But here's the thing. I'm going to leave campus shortly after 6. I'm going out of town for about a week. If I don't have your exam in hand, I'm probably going to give you a 0. And then we'll have to figure out if you do get it, like you get it done at 6:30, but I've already picked them up. You're going to get a 0 at that point, and I'll just file a grade change whenever I do actually get back in town and pick up your exam and grade it. I can do that, but I don't think you're going to like that. So let's not do that. Have your exam done right at or as close to 6 as you can. And that way I've got it, I can get it graded, and I can accurately get your grades entered. Okay. Um, let's not do the alternative, right? And now the other alternative is, at least let's not do the alternative where you get it done after 6. Let's not do that. You're not going to like the results of that. Or you can uh, you can take it with me from 3 to 5 p.m. Thursday. Just email me. Let me know you're going to take it with me so I can print enough copies. All right. So again, all this information is um, in Canvas. Go look at it. Let me know what questions you have. If something's not clear, get it done before 6 p.m. on Thursday. Okay. What else then? As we mentioned, it is comprehensive. Comprehensive is comprehensive. Bu- 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 So that means basically it's chapters 1 through, I'm going to say 10, but not 9, because we didn't talk about chapter 9. I mentioned briefly chapter 9 is exergy, and it's just kind of I think it's a silly topic. I get it, but it's not something I'm going to spend class time on. Um, and then not unsteady flow, right? Not section 5.5. That was unsteady flow. It's a cool topic. It's neat to talk about, but not on there. Not the diesel cycle. There will be an auto cycle problem on there. Right. So it's going to be 5 problems. Typically it's like I don't know, like a chapter, like there's basically 5 problems. One of those is going to be an auto cycle. One of them will have some isentropic efficiency component. So basically, it's like there's 2 exam 2 level problems. There's 2 exam 3 level problems. One of the exam 3 level problems will have an isentropic efficiency component added to it, and then there will be an auto cycle problem. That's normally kind of how this breaks out. Um, it'll be a combination of closed systems, control volumes, possibly heat engine stuff like that. Um, Yeah, so all that's, I mean, that's all included here. So it's all kind of fair game in there. I'm not intentionally going to try to trick you or make it difficult. It's just it is a comprehensive subject. So there's a lot there. 5 problems. They're 25 points each. And if you look on Canvas, I've tried to make it very clear how I'm going to grade those. I will only grade 4. And you're welcome to ask. Well, can I do all of them and you pick the highest one? Nope, I will only grade 4. What that means is I will only grade your 5th problem if you um, if you leave a problem blank or mark a large X through a problem you want me to skip. That is the only reason I will grade your 5th problem. I'm going to try to get them done fairly quickly. Normally, I've got a lot more to grade. I don't have too many this semester, but those are the rules. I'm not going to change those just because I got a small section this semester. I will only grade your 5th problem if you tell me to. How do you tell me to? Look at a problem, say nope, and you leave it blank, or you look at a problem, get started, and you're like, nope, and you just draw a big X through it. Otherwise, what I've got is I've got a system that I basically, if you put a big X on a problem or you leave a problem blank, I'll flip to your 5th problem. I'll put a little check mark in the bottom corner of it, and that tells me when I get to the 5th problems, I need to actually grade it. If there's not a check, I close your exam up and I don't grade your 5th problem and I told your score out. If I go back later and I realize, I didn't, I've only scored 3 problems. I missed the check. I'll grade your 5th problem. But at any rate, I'm only going to grade 4. Hopefully that's clear. If there's any questions, feel free to send them to me, but I'm probably just going to point back to the statement and say, I'm only going to grade 4. You're welcome to ask. Every possible way. I've seen every possible way to ask questions about that over the years. I'm going to grade four problems. I will only grade your fifth problem if you tell me to. Okay. All right. So you get 2 hours and you only have to work four problems. That's not too bad. That's kind of like what we did with for exam three. So yeah, you do need to keep moving. Keep in mind how I grade these. You show me, how to solve the problem. That gets most of the points. That's not going to change. I'll grade these very similar too. If you look at the auto cycle and you're like, Steve, those auto cycles, they take forever. How am I going to get that done in three other problems in 2 hours? Well, yeah, if you look at the example we worked on the auto cycle, we were looking for five different things or four or five different things. If I ask you just one or two things about a problem with the auto cycle, and if I'm strategic about what I ask, I can ask you to find me just two or three things, or normally just one or two things around the auto cycle, and it can require you to do enough math to show me, how to navigate the problem of the auto cycle effectively, and I can still assess that you can do that without asking you to spend 2 hours doing a ton of algebra to find five different things. So all that to say, if you know how to do the really long auto cycle problems, you'll be able to do. Again, I'm just going to ask you for two or three things instead of four or five. So just keep that in mind. Don't let that panic you. And again, remember, don't leave a problem blank. Show me that you know what the fundamental equations needed to solve that problem are, and go with that. All right, I'm going to make sure I didn't miss something here logistically. What can you use? It's in the testing center. You can take it with me. It's comprehensive. Um, five problems. Those are the things. I think that's logistically how the final works. I can't think of anything that I'm missing there. So we'll keep moving. As far as topics, we'll quickly go through basically the whole course in just no more than an hour or so. Topics. I normally start at chapter three. Chapters one and two are good. No, by the way, no manometers, right? Uh, some of you guys maybe are jumping for joy. No manometers. You'll get those again in fluid mechanics, right? So no manometers. So yeah, but so normally I start at chapter three. It's not that chapter one and two are not critical or important. They are, but chapter three is really where we start picking up the meat and we start hitting our course learning outcomes. So, identifying properties of pure substances. Right? Well, remember when I first introduced this in chapter three about using property tables, I said there's like a four-step process. And the first 100 times or so you do it, you want to refer back to this process. And then after that, the next 1,000 or so times, you probably get used to it. And a lot of times when it's an actual face-to-face class, people kind of chuckle. They think I'm kidding about the next 1,000 times. And now that you guys have made it through the class, you get it. I'm not entirely kidding there, right? You want to be pretty good at this. Now, we've added some flavors, right? Um, Step one was identify your substance. That has not changed. What has changed is now we kind of have some branches. There's some choose your own adventure going on here. For water and R134A, right, it's going to look like this. And I mean, for all of them, right, from one, and then step two is then record known properties. That doesn't change no matter what flavor you're in. Step one is identify your substance. Step two is record known properties. Now, if it's water R134, step three is basically determine the phase is the most important thing for us, which basically means which table, which row am I using? Because I'm going to use property tables. I need to know two properties. I either need to know P or T, and I need to know V, U, H, or S. And I've got this diagram. And everything on the left is liquid, everything on the right is superheated vapor, everything in the middle is a saturated mixture. All right. Here you got X, right? X between 1 and 0. Right? That's where X is equal to whatever value you're looking for. In this case, maybe we say U minus U sub F divided by UFG or UG minus UF. Okay? That's if you have a mixture. So if you have a saturated mixture. That's if you're in the dome region. If you're to the right of the dome, you've got superheated vapor. To the left of the dome, you've got compressed liquids. Follow the appropriate rules for those particular phases. If I'm given P and T, then I've got this curve. And then it's just simply, I'm either on the dome, which means it's saturated something, and I got to figure out another property to figure out the quality, or it's to the left of the curve, that means it's liquid. To the right of the curve, it's superheated vapor. Right? So that's 3 for water in R134, and then common steps of record basically desired properties at that point. Right? Record desired properties. Now, if it's an ideal gas, PV is equal to RT, and delta U is equal to the integral from T1 to T2 C sub V dt, and delta H is equal to the integral from T1 to T2 C sub P dt, which we normally don't do the integral. We normally just approximate this as C sub P, right? Yeah, so we would say I could do delta U. We could approximate that where I say C sub V at the average temperature is a nice constant value multiplied then by the change in temperature. I could do the same thing for delta H, right? I could use table properties also for U's and H's because they are just functions of temperature. So I've got tables that have, right, U and H are functions of temperature. Seen here using specific heats. Or I can use tables where the tables are functions of temperature and get U and H that way. That's perfectly fine. For S, we use Gibbs equation, which we'll talk about later when we talk about chapter 7 stuff. All right, so that's how we get U's, H's, and we use Gibbs equation for S. And if I need to relate PV and T to each other, it's a linear relationship using the ideal gas law. Okay. For solids and liquids, okay. For solids and liquids, if and only if phase is constant, because if phase is not constant, the specific heat is not constant, and therefore this does not apply. We will do delta U is approximately, they use C sub P in your text, delta T for solids and liquids. If I need to know the change in enthalpy, like if I've got flowing liquid, that's equal to C sub P delta T is normally all we need to worry about. But if there's a pressure change, you can also incorporate the pressure change. Those of you who went on and looked at the Rankine cycle, we're looking at an ideal isentropic pump to maintain the Rankine cycle, and that if it's isentropic, that means there's no temperature change because it's constant entropy. But there is a pressure change in an ideal pump, so it depends on what you're dealing with. It's pretty rare you need to worry about delta H for solids at all, and it's not too bad for liquids, and it's normally just this. Okay, you'll have to encounter that. I don't think I've put a solid liquid constant phase situation on the final. I say that. I mean, I don't. I'm also being very clear here. I'm not guaranteeing that, but I don't recall doing that. It is fair game, but I don't recall doing that. So again, a lot more. It's pretty much it hasn't changed for water in R134. What is your substance? Record known properties, determine the phase, use the phase to figure out which table, which row, record desired properties. We have added some complexity now. We understand we can use ideal gases, but the same basic process. This basically replaces step three here, and the same thing down here for solids and liquids. This replaces step three for solids and liquids. Step four is common. After you figured out what you need to know, record desired properties, plug that into first and or second law equations accordingly. Also, um, just like with ideal gas for S values, we're going to use Gibbs equation. Okay. So that's chapter three plus some stuff from chapter four to help us describe ideal gases and solids and liquids, because that was not our focus in chapter three yet. And that moves us then to heavily into chapter four. Chapter four and five is where we really focus on the first law. Chapter four, we focus on first law for closed stationary systems. Chapter five, we focus on first law for steady flow control volumes. Now, I don't want to forget, um, moving into chapter four, there is, when we're talking about closed systems, it's not uncommon we'll encounter a boundary work situation, a compressible system. That is if V1 is not V2. If I've got a system that has a total volume and that total volume changes, that volume does not change spontaneously. For that volume to change, force must be applied. If a force is being applied, that means work is being done. We can compute the work in the out direction based on that volume change, where we integrate what actually causes the force, because work is the integral of force times distance. So what causes the force when the boundary is changing or the volume of a system changes? Well, it's pressure, either external or external pressure is going to drive that volume of the system change. So now pressure alone is not energy, this is energy. But if I integrate the effect of that pressure across an entire change in volume, that net result will give me the boundary work. So these are typically the main situations we might encounter would be constant pressure. It might be polytropic. Right? We saw all these in chapter four between homework and or examples. It might be a linear situation. Right? That's where P is equal to some basically slope, some constant value times volume, plus basically kind of an initial pressure, a y-intercept, if you will, a B value. And it might not be A and B. It's some constant times V plus some other constant, some linear form of an equation. These are the main ones. These are the ones I would test you on. There are others we can encounter. Again, polytropic, we saw that is P times V to some power, constant power N is equal to another constant C. So that's a simple enough integral. There are, I've mentioned this before, there are pre-derived equations that you can use. If you're allergic to the calculus, if you don't want to plug this in and do an integral, that has been done for you. But if you're allergic to calculus, I would probably get that checked out and taken care of. But at any rate, we don't do a ton of calculus. I just need you to be able to do it when we do it. That's boundary work. If the volume of a system changes, I do need to be able to figure out how much energy is required to cause that change, or that is exerted as a result of that change. So from there, then if we talk about first law, and specifically if we want to focus on closed stationary systems. First law for closed stationary systems. Well, if we start back at the most basic original version of the first law, E dot in minus E dot out is equal to dE for my system dt. The change, or I'm sorry, the rate at which energy comes into the system minus the rate at which energy goes out of the system is equal to the change in the energy of my system with respect to time. Again, conservation laws take this form of in minus out equals change. I always try to write that in red. That should Whenever you see a conservation law, a big red alarm bell should go off. In minus out equals change, right? The rate in minus the rate out equals the rate of change. Now, if I'm dealing with a closed system, I'm probably not so worried about every little differential change in time. What I'm normally probably going to do is I'm probably going to want to know about what is the total amount over a particular period in time. So that's what we're going to do here. We're going to say, you know what? Let's just focus on a total energy change for my system over a total period of time. And what's going to happen is I'm going to multiply my time by my rates. Well, if I multiply time by my rates, I get total amounts. So the dots go away because I've multiplied by time. The dot indicates that's per unit time. Multiply that by time. Now I just get total amounts. The energy in minus the energy out is still equal to the change in the energy. It's just no longer am I measuring per unit time. And we talked about what are the different ways that energy can cross the boundary. And if you all were sitting in front of me in a classroom, I'd say, what are the three kinds of energy that can cross the boundary? And I would wait until I would get answers I like. And that'd be heat, work, and that could be mass. And I could have all those things going out. So I'm going to add the in, subtract the out. So minus Q out, minus the work out, minus the energy of the mass out. And keen observers might say, Steve, you said closed systems. Yes, that is correct. I do that to remind us that is a form of energy that can cross the boundary, but in a closed system, there's no mass crossing the boundary. Therefore, there's no energy being lost or gained by mass crossing the boundary. So those go away. That's equal to all the kinds of energy that can change. Well, there are three kinds of energy that can change. That could be internal energy. Again, mass is constant, so I'm going to factor that out. Could be kinetic energy. Could be potential energy. I'm writing in the margins, which I hate doing, but here we are. And if it's stationary, it's not changing kinetic or potential energy. If it's closed, these go away. And if it's stationary, these go away. That leaves me with Q in minus Q out plus work in minus work out is equal to M delta U. And again, a common way this can be written is Q net in, that's the difference between Q in and Q out, minus W net out, the difference between work out and work in, is equal to M delta U. It's a very common way it'll be presented in a lot of thermodynamics texts. Your text takes it this route where we say, you know what, let's just consistently add the ins, subtract the outs. This route says, well, add the heat in and add the work out, and plug it in accordingly, and then the signs take care of themselves. And it works if you're used to that. If you're not used to that, it's a bit confusing. This is not so confusing. This is the reason your book approaches it this way. Add the energies in, subtract the energies out. Okay. Either way is correct. You just got to keep track of, am I adding energy to the system or am I subtracting it? The sign has to make sure that works. That's first law for closed stationary systems. Now, if we want to look at first law for steady flow control volumes, well, first we got to make sure we understand what steady flow means. Now, if we introduce, because I've got control volumes, if I introduce conservation of mass is that if I add up all of the mass flow rate coming into my system, and I subtract where I add up all of the mass flow rates going out of the system, that equals the change in the mass for my system with respect to time. Again, in minus out equals change. For steady flow, everything with respect to time goes to zero. Everything's constant with respect to time. So that means that the total mass flow rate in is equal to the total mass flow rate out for steady flow. And this is common because we don't have a lot of tools to work with differential equations yet, I'll leave that for later courses. This is very common. What we're going to do is we're going to assume that everything's flowing steady. We're going to be working with steady flow systems if it's a control volume. So the mass flow rate in is going to, the total mass flow rate in is going to equal the total mass flow rate out. And then it can simplify a little further for one inlet, we'll call it 1, and one outlet, we'll call it 2. M dot 1 equals M dot 2, which we'll just call M dot. Now, if I go back to first law for steady flow control volumes, now that I've talked about conservation of mass, because I'm dealing with moving mass, so I got to make sure the mass is conserved in addition to the energy now. So if we look at the first law for control volumes, that's going to equal the, well, we start back at the first law, original version. E dot in minus E dot out equals dE for my system, dt. And again, because it's steady flow, dE dt is going to go to 0. So now I've just got stuff coming in and stuff going out, set it equal to the change for the whole system being 0. So what does that mean? Well, that means that I've got the rate at which heat comes in. So all these are per unit time right now. The rate at which heat comes in, the rate at which work comes in, we call that power, the power input, plus the energy of mass coming in. So I'm going to write this as the summation across all the inlets, m dot times h plus v squared over 2. And then I'm going to neglect the potential energy because we've talked about that before. We normally just neglect the potential energy unless it's a massive system. And I'm going to subtract all these things going out. Q dot out minus the power output minus summation across all of the outlets. M dot times quantity H plus V squared over 2. That's heat in, power input, energy of mass coming in, and then subtract all those things going out. For a steady flow control volume, that whole sum is equal to the change. For steady flow control volume, the change is 0. This is the general version of first law for control volumes, steady flow control volumes. This one always works. If I happen to have for one inlet and one outlet, then this does simplify a bit more. Then I've got Q dot in plus the power input. I'm going to go grab these guys. So minus Q dot out minus the power output. I'm going to group the energy of the mass in and the energy of the mass out together. It's a common m dot for the two of them. We talked about that here. It's m dot 1 is equal to m dot 2 is equal to m dot. So I'm just going to factor out the common m dot. And I'm going to multiply this by quantity h1 minus h2. Again, that's in minus out. Plus v1 squared minus v2 squared, both over 2. Kinetic energy in minus kinetic energy out. And that sum is going to be 0 for a steady flow control volume. So again, add the energy in, subtract the energy out, set that equal to the change. For steady flow control volume, the change is 0. So that's heat, work, and energy of mass coming in. We've talked about dealing with the kinetic energy terms. There's kind of a checklist I try to give you guys about should I consider those. It's basically, is it given? Is it important? Like in a nozzle and a diffuser, it is important. Other devices, maybe it's not critical. But if it's given to you, incorporate it. If it's asked for, try to find a way to find it. Those are kind of basically the way that works. All right. As rapidly as possible, that's chapters 1 through 5. Let's talk briefly about 6. Chapter 6, we introduce the concept of devices that lead us to the conclusions of the second law before we actually get to the second law. So there's this concept of the heat engine. So we were aware kind of in the 1800s that mechanical energy was conserved. But we knew heat was energy, but we couldn't figure out How could we get all of heat to turn into work or turn into power and turn into mechanical energy? Conservation of energy principle says I should be able to do that. A heat engine is a device that allows me to do some of that. So a heat engine is a device that's going to absorb heat at a high temperature from some high temperature source in a what we call a boiler. That boiler is going to kick out high pressure, high temperature steam into a turbine, and that turbine is going to extract work out. And that turbine then is going to feed low pressure, low quality steam to a condenser. That condenser is going to reject the remaining heat that could not be converted to work, and it's going to reject that to some low temperature sink. Now I need high pressure going into the turbine. There's nothing in the boiler that's going to increase pressure. In fact, it's actually going to lose pressure in most real boilers. Our ideal boilers we'll look at in this text, we're going to assume typically a constant pressure in the boiler. But all that to say, I need high pressure going into the boiler. How do I do that? I need a pump. And that pump is going to require small work input. If I get it all the way into liquid form, it doesn't take much power input or work input to get it up to a high pressure. It's ready to feed to the boiler. Process repeats. First law says that basically QH minus QL is equal to the net work out, the difference between work out and work in. That's what the first law will boil down to. The thermal efficiency for any heat engine is always going to be what you want, the net work out, divided by what you have to do to get it. That's QH. If I take this and plug it in here and massage the equation, that becomes 1 minus QL over QH. And if it's a reversible device, we can also find that thermal efficiency based entirely on the temperatures. That's 1 minus TL over TH. So that's our maximum performance, our maximum efficiency, but the efficiency for any heat engine is always the work divided by the heat in. But if it's reversible, we can also set it equal to that maximum limit. We also have, we talked about refrigerators, and its interesting cousin, the heat pump. Graphically, they're the same device. They take the same shape. What we're doing with them changes. But in both cases, we're talking about a device that moves heat from a low temperature object and puts it out into a higher temperature object. So a heat pump and a refrigerator are going to lose heat to a high temperature body. And here we're going to use what we call a condenser on top. All right, we're going to use a condenser on top. That condenser is going to get fed by a compressor. And I draw a turbo compressor typically, reverse of a turbo, putting work input. That is going to get fed by our low side heat exchanger, or low pressure side heat exchanger that we will call an evaporator. This is the cold coils. This is what's inside your house or on the inside of a refrigerator that we're blowing air through, and that cools the air down. It's doing that by removing heat from the low temperature source. So in the evaporator, we need the refrigerant, the working fluid, to be at a lower temperature than this low temperature sink that, or source that we're trying to absorb heat from. How we get there, you need some process that drops the pressure and the temperature from the basically from the outlet of the condenser to the inlet of the evaporator. Typically, the easiest way to do that is what we call an expansion valve. No moving parts. You just squeeze the flow and then you let it expand out. And as it expands, it goes to a lower pressure and lower temperature. We've talked before, you could plug a turbine in here. In a large industrial system, that might make sense. You might actually get enough work out to justify it. But that's normally moving parts that are going to wear out and have to be replaced and maintained. So that's a cost that's normally not worth it. In a small device, you're just going to have a little squeeze valve basically that throttles it and expands it. And that causes the pressure temperature drop, causes the refrigerant to change phase basically. And we get low temperature refrigerant flowing here that we can then absorb heat into. Okay. So same device for both refrigerators and heat pumps. In both cases, your first law looks like this. What do we got? We got your work in is going to equal basically your net heat out. That's going to be QH minus QL. And then from there, if we're looking at the refrigerator, the COP, the coefficient of performance for that refrigerator, it's always going to be what you want. In the case of a refrigerator, that's QL. Divided by what you have to do to get it, that's going to be work in. If I plug this in for work in, then this becomes 1 over QH over QL minus 1. And then the maximum coefficient of performance would occur for any reversible cycle. Carnot, again, I pointed to the Rankine cycle and said we didn't have time to look at it, but you could also apply this to a Rankine cycle. That's a reversible ideal cycle. If I've got a reversible ideal cycle, then the coefficient of performance is now where I replace this ratio of heat transfers with the ratio of absolute temperatures, 1 over the ratio of TH to TL minus 1. And if it's a heat pump, so these equations are applied to refrigerators. If I've got a heat pump, it's the same device. The only thing that changes is what I want. For a heat pump, I'm going to measure its performance based off of what I want. That's QH. In the case of a heat pump, I'm trying to heat the inside space, and I'm doing so by cooling or stealing heat from the low temperature source, typically outside air. I'm bringing heat in that way. So it's kind of the reverse of a refrigerator, but it's the same basic device. So again, coefficient of performance is what I want, QH, divided by what I have to do to get it. That's work in. Plugging this equation in for the work in and massaging this equation, this becomes 1 over 1 minus QL over QH. And then again, for the maximum value of that performance is going to occur anytime I've got a reversible cycle. And in that case, I can replace the ratio of heat transfers with the ratio of temperatures. Use Kelvins or Rankines there. Negative signs blow this up, so I can't use Celsius or Fahrenheit. All right. In a nutshell, those are the big things about Chapter 6. Again, in Chapter 6, we introduced the Carnot cycle, which is a reversible cycle that I can use for these reversible efficiencies or performances. And then later on, we talk about other cycles like Otto, Diesel, and Rankine, which are also reversible cycles. Now, how do we know reversible makes sense and that we can use these and that how do we know that's the best case scenario? That comes in when we talk about entropy, which is Chapter 7. Entropy. And that basically comes down to the second law. Our good friend Clausius came to the conclusion that if I were to integrate, if I'm to integrate across an entire cycle, the change in entropy, which just becomes 0. If I go around an entire cycle, the entropy of my system will go back to its initial point, back to 0. But what we find is if I also go around that same cycle, I'm always going to get that if I take this, I'm going to have this expression here where if I integrate all of the heat transfer divided by the temperature at which that heat transfer occurs, and I do that around the entire cycle, this quantity always ends up being negative. It's always less than this 0 that the entropy change comes back to, because for the system, it comes back to its initial state for it to maintain a cycle. If I go around that cycle and look at all the heat transfer divided by temperature added up, where I subtract the heat out, add the heat in, I get a negative quantity. And so what we find is that if I just look at a slice of that process, that entire cycle, what I'm actually measuring is a change in entropy. And that change in entropy is always greater than or equal to the heat transfer divided by temperature that causes that entropy change. Now, this is the raw form of the raw differential inequality form of the second law. what we normally do is we normally work with this equation version where I say, you know what, for a process from state 1 to 2, I'm going to integrate ds, that becomes delta S. And instead of an inequality, I'm going to make it an equation. I'm going to say it's equal to what happens when I add up, I integrate all of this heat divided by temperature. Go around from everywhere to get from state 1 to state 2, any heat transfer that occurs, divide that heat transfer by the temperature at which it occurs. And I acknowledge that this, the delta S, has to be bigger than this quantity. How much bigger? It's bigger by the amount of entropy that's generated. So everything we do generates entropy. That's the rule. Best we can tell, that is the rule for our universe. Everything that occurs generates more entropy, either in the system or in the surroundings. Somewhere I can get the system back to its initial state. I could possibly get the surroundings back to their initial state, but I can't get both the system and the surroundings back to their initial state. Time marches on. Things cannot go back where they were. Entropy is always generated. To the best of our knowledge, we cannot destroy entropy. Now, does that hold up at the quantum level? What happens when we go inside a black hole? I don't know any of these things. That's beyond me, and I'm okay with that. I know where my knowledge limit is, and I'm fine with it. If you go on into those kind of realms, I wish you well. We need people that can do that kind of stuff. But this is the second law in its applied form for a process from state 1 to 2. Right? Now, what can often happen is if we have heat occurring at a constant temperature, if you have heat transfer occurring at a constant temperature, that's the common thing we'll do with this integral is we're not going to do any crazy partial integrals. I promised you guys that, and that's not changing. Then this becomes the sum of Q, where Qn is positive, and anywhere you have heat transfer, you divide it by the temperature. So if I've got Qn, I take that, I add the heat in divided by the temperature. If I've got heat out, I subtract the heat out divided by the temperature, and this quantity replaces this integral. Right? So we've seen a couple of homework problems. There was a test exam 3 problem where we did that. So that's showed up a few times. If if something tells me the process is reversible, that's telling me it's not generating entropy. That means that is the limit. That is the closest we can get to the best real case scenario. Right? Which means that if everything in our cycle is reversible, that means I can operate at the highest level of performance. There, or back over here for a heat engine. So if all the devices around this cycle are not generating entropy, then these performance ratios apply. What that means is throughout the entire cycle, all the devices, none of them are generating entropy. Right? So, and we've talked about this before, adiabatic. Adiabatic does not mean isentropic. Reversible does not mean isentropic. Adiabatic and reversible does mean isentropic. I need both. Right? I need both adiabatic and reversible for it to be isentropic. And I've drawn the arrow. We've talked about why I draw the arrow. Right? This can be the opposite of that. These can add together to be 0, and this can be isentropic. That's a weird scenario, but it does happen. But if I know it's adiabatic and reversible, if I know this is 0 and this is 0, that means this is 0. Okay. Trying to keep this to kind of a standard 75-minute class period. I'm getting pretty close. Because the big thing we still got to talk about then is Gibbs equation. Because basically, those are what I've given you here is some basic tools I would deal with the different terms in this equation. This is either going to be 0 or I'm going to do this. I might say Q over T represents this quantity. Sgen is either going to be 0 or it's going to be what I'm solving for. What about delta S? What do we do with that guy? Well, delta S, I can either use property tables to find S values, or I can use Gibbs equation, which we've alluded to earlier. Gibbs equation allows us to approximate delta S. I have to have specific scenarios. So if I apply Gibbs equation to an ideal gas, delta S is equal to the integral from T1 to T2, C sub V dt over T. This one is plus R ln ratio of specific volumes. In the 10th edition of the text, you don't have to perform this integral. You have some options. In the 10th edition of the text, they give you these S plus values in the back of the book for ideal gases. You can use those. You still have to add this R ln, and these are, again, the rookie mistake is using speeds here. These are specific volumes. It's from the ideal gas law. I can also approximate this as C sub V at the average temperature. The rookie mistake is we just use cold temperature on this. We don't use cold temperature on this unless it's an Otto cycle. I need the average temperature. Given the average temperature, which means I need T1 and T2, or I need to guess and check. Given the average temperature, I approximate this as constant. Then it comes out of the integral. Now I'm integrating dt over t. That's natural log of T2 over T1. Keep this term R ln ratio of volumes. I can also do it this way. There's another version of the Gibbs equation where it's also equal to the integral from T1 to T2. This is C sub P dt over T. This one has minus R ln P2 over P1. Those are pressures. So using the pressure version, the exact equal sign where these are table properties, these are what we call S naught values, or what I call S naught values, or S circle, S0 values, whatever you call them. S naught 2 minus S naught 1, and this one keeps this minus R ln P2 over P1. We can, instead of using these table properties, I can approximate this with C sub P at the average temperature times the natural log of the ratio of temperatures. And this one still has the minus R ln P2 over P1. Either of these work. For solids and liquids, again, if phase is constant. If phase is not constant, specific heat's not constant, so this doesn't work. But if I'm dealing with a solid staying a solid or liquid staying a liquid, delta S can be, let's say, approximated as C sub P at the average temperature times the natural log of T2 over T1. What does this do? These are little s's. That means I can take M times little s2 minus little s1, which gives me big S2 minus big S1, which is equal to the integral dq over t plus s gen. And basically what I'm saying is these are little s's. So if I have an ideal gas, or if I had solid staying a solid, liquid staying a liquid, I can take these and plug them in for this here. To find the whole thing, I still need to know something about the heat transfer that's occurring and is it generating entropy? We hope they tell us it's the best case scenario. It's the maximum output for the turbine or minimum input for the compressor or something like that. Right. And then the last couple of things are what the homework's over, and we've just done lectures over those, isentropic efficiency and the Otto cycle. Like I said, those do show up on the final. No sense in hashing through those. You guys have just seen those recently. So, okay. That's what I've got. I'm going to hit stop recording here.